Ah, I run. Yeah. So, and I see a few people jump on today, and then we're gonna go through and do some stuff. Um, I'm not so sure what we're going to end up being able to do today, but most of it is going to be centered around looking at the code that we did today, yesterday, and basically understanding what we did yesterday and why we did it as we did it. That way we can sort of yeah. And also, anyways, Bartholomew has been asking for reviews here, and I think we can go through that and basically answer the questions so that we can go through. Okay, cool. And yeah, let's actually open that code. uh Zephyr project. What are we doing? Applications, Zephyr custom BLE subs, and then get diff, uh, get log p. Let's see. Yeah, so this is a diff we want to look at. Anyways, we can look at it online, and it might be easier. Yeah. So I've announced this. I think there's enough people joining, and I think let's go through the reviews. Let's explain what happened yesterday, and then perhaps find a way of testing what is happening on in the code, basically, if we can. And feel free to post questions either on Discord or on WhatsApp or on the YouTube chat. It's easier if you just use the YouTube chat, and I can see them quickly because then I have one place to look at, and I'm not looking at too many other messages. And I think I can say and we are live as always. Cool. So let's look at this. Let's look at Bartholomew's review. So the first one is, yeah, we shouldn't use, yeah, magic numbers. We should avoid using magic numbers, and I think that one is chill. That one is chill. Wait, Control E. Yeah, audio service. Let's see, and I think this is the one that we want to remove. So should be num tabs. Yes, please. Yes. Yeah. Thank you. Thank you. So that's a good one. Thank you, Bartholomew. Should we just look at the? Should we look at the diff, and then after we look at the diff, we can go back to doing the reviews. So yeah, let's start looking at the diff. All the things that changed. I think all the things that changed. Let's look at everything that changed, and then we'll go from there. So number one, today we ended up adding kconfig for Kimsys DSP filtering, so that we could use the FIR filter function. That way we can, as Kimsys DSP, uh, yeah, no, I wanted the web. Yeah, so yeah, we want to use this function. We want to use basically filtering functions. Relax. So we want to use filtering functions, and in order to use filtering functions, we need to enable them in kconfig in Zephyr here. I just want to break down these changes. So Zephyr has yeah, it's loading. It's slower. So Zephyr has Kimsys DSP, yeah, DSP underscore. So there's this 24 options. You can add all of this basic math, blah 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 blah. But what we added yesterday was Kimsys DSP filtering. So this just enables us to use filtering functions from Kimsys DSP, and that's why that line is there. Cool. So we've seen that one. And then the other thing that we did here is I will just remove comments from now. Don't show comments for now, so that we just. And the other thing we did is we use this filter that we defined from, if I recall correctly, where's my Discord? We use that filter that we designed from FIR.com. FIR.com. So here we use this to build our filter rather than the one that we used before. And I think, no, this is not the one that we did. And rather than the one that we did before, because the one that we did before was it gave us really giant numbers, and this one enabled us to give us normalized numbers from -1 to +1. Although I did find like a 40 and a 30 in there, so I don't know about it. But basically, the scaling of the scale, yeah, there's these ones, and there's this ones, yeah. The scaling of the coefficients that we had before were too giant, and they were basically causing a direct crash whenever we tried to run the filter yesterday, and that's why the app was crashing so much. So we moved from that and we moved to this, and I know this is the one that we just fixed in here. That's the other thing we added. We moved to this filter, so this is a better filter for us. Those tabs are better. And then we moved the instantiation of the filter and the initialization of the filter so that we do it only once at the beginning of the thread, rather than doing it at every iteration of the thread. We did that. And then after that, we removed our old root mean square calculations, and now we applied our filter. And basically all we did here was convert our samples into floats. I really still don't like this, that we have to go through each sample at a time. And I guess that's why you need like a super fast CPU. That way you can sample and do operations really quickly before you have to sample audio again. Because if you're sampling audio at 44,000 hertz, 44 kilohertz. Yeah, if you're sampling audio at 44 kilohertz and your CPU is running at like 200 megahertz, then you have enough time to do all of this. We basically have enough cycles to do all of this data preparation and all of that stuff. Data preparation and gathering and filtering and putting it, and kind of like inference, if you want to call it that. So that's what we did. We went through all the samples, and then with each sample we'd we would left shift it so that we get rid of all the, because remember, the audio is 24-bit data in a 32-bit word. So there's all of this 8 bits at the end and it's left aligned. In our microphone right now, we are connecting a lot. How do I say this? We're connecting a positive signal to the left or right. So we have the data left aligned. And what we did is we shifted the stuff to the right, so that we only have a 24-bit value within this 32-bit. And then we convert that 24-bit value we normalize it between 1 and -1. So that's what's happening here once we normalize it. And then below here we go through all the samples, and then we hand them over to our filter, and then the filter does some sampling, some filtering, and then it gives us back a filtered, it basically loads this filtered sample. Where is it? At some point we do make this filtered samples. At some point we do construct them. I do not see them. They're probably at the top. Filtered samples. Yeah, so we basically fill the filtered samples buffer with samples. Another thing you might have noticed if you're on this stream yesterday is that yesterday I was using block size, but block size is kind of it's the same thing, but we're counting rather than counting block size is bytes, and each filter is made of 4 bytes. So block size was counting, the block size that we were using yesterday was actually wrong because it was giving us the amount of bytes in the data rather than giving us the amount of samples that we needed to operate on. Because remember, each sample is 4 bytes. Okay. So there's all of that. That's really it. That's really the review. This is all we added. And if I run this code, you will see that we actually do get some output out of it. And this kind of is the reason I am not confident in it. Or rather, I am confident in it. It's just, I don't know how to use it yet, but let's see. And then we will run, and then we will apply the reviews that were given to us by Bartholomew. So get west build dash b nrf 52840 dongle nrf 52840 dash p always. I can always just do dash pristine. Let's see if that just lets me go. Activate. Yeah, so that actually does let me do it, so that's fine. And then I'll do Control C and then Control R and then ACMO and then that. So let's see, we shouldn't look at that, we should look at this. It's building. If anyone has any questions or such, please do give them. Please do post them. Oh my god, this build is slow, eh? This build is slow. Okay, so the other thing I would like to do is try and use GNUplot. So there's this application called GNUplot. I never know whether to say GNU or GNU. So GNUplot. I want to use GNUplot, and then yeah. So there's this. This actually enables us to plot all our signals. So I might actually just want to, because I already normalize before I pass them in into the filter. I might actually want. You can actually do the same. The two things you can plot the samples, the filter itself and the filter. You can, but how do I make it so that it can be, so that you can plot? Anyways, we'll see. We might have to just plot. We might have to plot the non-filtered ones and then plot the filtered ones and then keep the plots in between. But that doesn't sound cool. It would be more interesting to plot both of them. I don't know how we might be able to do that, but we'll see. Yeah. Let's see. It's probably built. Yes. Control R dash HW. Cool. That parks it, and then I'll put this on. I'll put this in bootloader mode, and then Control R. We can do DFU, and then that should load it into the app for sure. It should make it work. Okay, cool. So that's in. What's the other part? What's the other part? Yeah, so cool. Let's run that. That's on. And then we should see now if I connect to Bluetooth. If I connect to Bluetooth. In just a moment. So if I connect to Bluetooth and activate the microphone, it should go. Okay, connect. Bluetooth connected, and you can see we're getting filtered sample, and we're getting like, oh yeah, that's a problem. If we have to print them out like that, the messages are dropped. That's a lot of messages dropped. Yeah, and what are we doing? Why did we do that? Connect. Oh, wait. Oh, wait. The application crashes. The application crashes. So let's actually stop that. Let's actually fix that for sure. So the app crashes. So why did we just do let's see. Filter log dash log dash one, and then we'll say filter the block, because it feels like this does actually crash. I wonder if it's because of that or because of something else, but let's see. Okay, yeah. So we should get three at a time. Yeah. What do I want to do? Let's build. Okay, cool. So as that is building, let's keep looking. Let's now actually go back and look at the comments from Bartholomew. Let's actually let's go back and look at the comments from Bartholomew and see what he wanted. So the first question here is, maybe I don't see the whole picture, but why do we need this loop? This implementation calls k-memslab free and memslab void memblock 3 times. And there's a double free problem. So that's actually a really good question. So this is something that bugged us for quite a while in the beginnings of the team. And basically the I2S, let me see, I should probably have it here. The I2S driver. Hey Nathan, how are you? I'm just reviewing the changes I made yesterday on the Zephyr app. Actually, I'm not reviewing, I'm just walking through I2S common. I'm just going through the reviews that Bartholomew left. I think, yeah, then there's that. So the first thing you need to understand about this part is that number one, let's actually go back. So let's understand why we're doing that free 3 times. So when we're using memslabs, I think this is where I understood it. When we're using memslabs, you need to add at least 2 more. Okay, when you're using memslabs with memblocks, so Zephyr memslabs. So when you're using memslabs, yeah, when you're using memslabs, you provision blocks in it, yeah, And the thing is, you need to give it more than, it must be greater than 0, and then you need to, I think if I remember correctly, you need to give it more than 2 blocks. At least 2 more blocks. So it needs to have at least 3 blocks. Basically, if you read through this, there was a whole week where we debugged MEMS labs. But if you read through that, you will realize that whenever we're using a MEMS lab, you need to give it at least 3 mem blocks. Okay? And then, if you think about it, we want to record, we want to end up doing keyword recognition, or rather keyword spotting. And keyword spotting is when you do something like, if I show you my phone and I go like, let's just do that. Keyword spotting is when you do something like, hey Siri, or something like that. Hey Siri. She doesn't go on. Hey Siri. That's funny. Okay, hey Siri. You see when Siri reacts? Hey Siri. When Siri reacts, that's a keyword. There's a microphone that is listening for certain frequencies, or it's doing, I don't know if they're using MFCC, but it's looking for frequencies in my audio, and it's matching those frequencies in my audio to something that matches hey Siri. And then when you do hey Siri, you basically wake the processor up and it can receive commands from you. So in order to do keyword recognition, you want around 400 to between at least 400 milliseconds of audio. Okay, cool. So if you want 400 milliseconds of audio, you want to make a memory slab that can hold that many samples. Let's do the calculations. So we are doing one channel. We're recording from one channel, okay? And then from each channel, we want to record how many samples. If we're recording, I'll use Nathan's favorite tool, Excalibur. I don't know how to delete this. Can I delete this? Control A. This project is dead now. Can I delete? Yeah, and Control A. Delete. Stop laughing at me, Nathan, man. I don't know how to do this, but I need, you know what? It's easier to just do it. New private window, Excalibur. Excalibur.com. Did I just Google a domain? Yeah, so let's do a new one. Can we do something new? Yeah, that's fine. So let's think about it. We're doing 44, no. We're doing, we're doing 44 kilohertz. So what does that mean? We're recording 44 100 samples per second. Okay? But we don't want 44 100 samples because we don't want a full second of audio. We actually want 300 milliseconds, and 300 milliseconds is around a third or a quarter. So let's put it 400 milliseconds. Let's say 400 milliseconds, that's around a quarter. So 44 100, the calculator. 44, I should have used the calculator from the beginning. So if we're recording 44 100 samples per second, If we divide this by 4, it should come to something like 17,000. Okay. What if we divide it by 3? Where am I missing this? So we're doing 100 samples per second, but we only want 400 milliseconds. So how many there's only how many milliseconds? There's 1,000 milliseconds in 1,000 milliseconds in. So anyways, so that's 300 divided by 1,000 equals 0.3, and then times 100 is equal to what? It's the same thing. It's around 13,000. So basically, we want to collect around 13,230 samples. That represents 300 milliseconds of audio. 300 milliseconds of audio is enough to put in a phrased keyword. Something like, how do we call this thing? What do we call it? You can say Jarvis, okay? Like Jarvis, wake up, or something like that. Hey Jarvis, or you can just say Jarvis. So the reason we have that is because the I2S driver. So let's go back to Zephyr code now. Zephyr I2S driver, and then I can show why it's not a double free. So the I2S driver, what this does is, where can I see the source of this, if possible? Can I get the source of this? I2S read. I would like I2S read. Give me the I2S read function so that I can go to the source. I2S read. It should be in common. No. Yeah, but I want I2S. Basically, if you go to the I2S common, I think. I know what I want to show you. I just don't remember where it is. But the thing is, I2S, I expect you to give it a memory slab, and then it expects you to do the freeing. It will do the initialization. Okay. Our memory slab, I2S expects you to give it a memory block. It will do the initialization and it will put the data inside of it. And then we on our end are expected to do the freeing, and we need to consume the data and free it. So here, basically, if I go back to my code, so here, this loop, this 3 times loop, is because each loop is on a mem block. We're collecting mem blocks, and each mem block is 100 milliseconds of data. We're collecting mem blocks from our mem slab, and we use a mem block and then we free it. If we do not free this mem block, if you go back in the streams enough, you will find 2 or 3 streams where every time we attempted to do this, the application would run out of memory very shortly. We can actually do this right now. And see what happens. So I will actually remove the filtering. Let me remove the filtering so that you see. I will remove the filtering, and then I will remove this, and I will also remove this. And I will show you what happens. And then here I will say log 1 consume samples. So again, we can do a long build. Anyone has questions while that is building? So that we see why we need that mem slab free. And anyways, I can probably go back and find I2S and FRX. I know where to find this. Be patient. GitHub, Zephyr project, Zephyr. Let's go in there. And we want to go drivers. I'll show you. And then in it's building, and I'm looking for a specific file while it's building, so I can. I want to look at NRFX, yes, yeah. I think the read function is defined in here. I think you define read here and then you give it up to memslab. Yeah. Let's look for this mem block. Let's see where it is. I think that's all of them. No. It's somewhere. It's somewhere in here. So gets the mem block. No, that's fine. That's okay. Mem block released. No, that's fine. It actually does do it for us, or maybe it happens in I2S common. Could be I2S common. Does this bring in I2S common? Does this bring in I2S common? No. Okay, let's see I2S common. I2S common. Let's see. I want to see if there's a mem block. Let's find. Yeah. It reads it and then it frees it. But I want to show you where it wants to write it. Yeah, you see it allocates it here when it's going to write it. It allocates it. I2S common allocates the mem block. This is the mem block we give it to it. And then I remember it's documented somewhere. I really remember it's documented somewhere. But the I2S driver expects you to free this mem block. And in turn, so that built. Let's pack it. In turn, let's pack it. Cool. And then put this guy in bootloader mode. Let's DFU and upload that thing. And then what I want to do is come back and after it's done, we'll run it. And I'll show you a crash. But basically what I'm trying to explain is that I2S expects you to free that thing. Yeah, okay, cool. So look at this. If I connect to Bluetooth and I activate the microphone, look at you see what's happening? We're slowly failing. We sense audio, and then at some point it just dies. It goes like no. It goes like there's no data. It can't allocate the buffer. It can't use that buffer. So I2S expects you to give it a mem block. It will allocate that mem block and then it will use it. But if you haven't cleared that mem block, if you have not cleared that mem block, this is what happens. If you have not cleared that mem block, this is what happens. So cool. So if we come back here, we've removed the filtering for now. If we come back here and we remove the filtering and we rebuild that, see what happens. Bartholomew, you're here now. I was trying to explain why kmemslab is being freed. But basically, this code is running when we have removed the memslab. This code is running right now when we have removed the memslab freeing. And what is happening is I can actually, let's just restart it again so that Bartholomew sees. Yeah, it's on. Let's connect. If I connect to it right now, without that KMEM slab free that Bartholomew was commenting about, see what happens. So very shortly, we start running out of buffers. And then a bit after that, the I squared S starts failing completely. Okay? And this, the fix for this is exactly this code here. This code Bartholomew is asking, why are we doing? See, we're doing a free with every block so that the block is available to the I squared S thing. I squared S thing. Okay, cool. So let me go back and let's enable it. Yeah, we've enabled it. Let's build with it. Yeah, it's building. And I remember, yeah. So I don't remember if it's the I squared S. Wait. Maybe it even says it. Maybe I can find the documentation while that thing is building. FIR I2S. So it expects you to give it. I remember this now. I can go back to some older documentation. The older documentation was better here. So the older documentation was better, and it expected, if I can find where I read that, that's the problem. I always read these things and then I forget where I read them because now I know them. Configure, read. Read data from the RX queue. Data received by the I2S interface is stored in the RX queue consisting of memory blocks pre-allocated by this function, RX. Okay. Ownership of the RX memory block is passed on to the user application, which has to release it. Do you see that, Nathan? I mean, not Nathan. Bartholomew. Do you see that? That's why we're doing that free of every mem block. That's exactly why we're doing that free. We share ownership of this mem block. We share ownership. This particular mem block that we're operating on here. This the one that is the current one. We're doing 3 so that we can get 300 milliseconds of data. This particular mem block that we're operating on right now, we share it. We share the ownership of this mem block with the I squared S peripheral. And the I squared S peripheral expects us to release it. If we don't release that mem block, what happens is our application runs out of memory. Okay? So now I've gone back to the version that I had before. I'm not applying the filter yet, but I've gone back to the version that I had before, and it's built here. Let's quickly dump that into the application, into the board, and see what happens. Yeah. Nathan's laughing at me again. So let's dump that into the board, and then let's see what happens. And then if that fixes it, then we resolve that PR review. Okay, that should give us something. Okay, cool. And then I'm gonna connect to that, and then if I connect now, you'll notice now it can go on forever. It doesn't run out of memory because we're doing the thing that the I squared S thing was expecting us to do. By the way, this wasn't so easy to find. This took me long to find. I can promise you, this took me long to find. This took me like 5 or 6 streams. It was a whole week of like trying to get the app not to run out of data, and I had to. That's how I went back and found that information. Okay, so now My math skills are not good. Okay? My math skills are not good. They're not as good as I would like them to be. Or rather, I think Bartholomew's math skills are better than mine, to be honest. But what am I saying here? I think we have a filter. We really do have a filter. We have a filter, and most of this filter is actually sorry about that. Most of this filter has actually been built by not us. What we are doing is we're taking work by people who know filters very well, and then we're composing that work into something that we can sort of do oh my word. Sorry. OBS is confusing me. We're taking that filter and we're composing it into a filter that we're using in our own work. However, we just realized at the beginning of the stream that the app was crashing whenever we did this. So what I want to do right now is just to apply the filter and not log anything out and see if that actually goes on for long, because I have a feeling I was making it run out of like buffers by doing the thing I was doing. So I just want to log out that, hey, we've actually filtered this thing and this is the correct result. Once we've filtered it, then we can think about how we're going to test it. And I think one of the ways is either get very good at math so that we can just do actual calculations on paper and prove this thing out using proofs. Or maybe there's this option that I've been exploring. We can plot the signals, but now I don't know how to use NuPlot in combination with a serial. We only have one serial interface. I want to send the filtered sample and I want to send the actual sample, and then I want to plot both of them. But I don't know how to tell NuPlot to go like. I could send filtered sample. We'll see. We will see. Just give me a moment. We will see once we get to that. So let's do this and see how many blocks it filters, and then we can go on after that. Let's build it. First of all, just to make sure filtering is working all the time, and it's not like causing like a crash. If it's not hay fever, it's hiccups. If it's not hiccups, it's hay fever. If it's oh no. Sometimes it's my wife trying to cook, and I don't know. It's just life is hard when you're doing live streaming. Okay. Any questions so far? Any questions so far while you guys are here? Any questions while we're building? We can just ask questions. Ask questions. Any sort of. If you don't ask questions, I'm going to ask you questions. Nathan, what are you working on? Bartholomew, did the CPU work on your FPGA? That's from the other stream. I probably need to get faster internet because I think my YouTube Studio hangs or something, and then I don't get messages that quickly. It's building. It's building. It's building. It's building. It's building. Cool. What ideally I would like to implement is something that some way of. Okay, let's see that one. Once this is done, then we can go forward. Once we know it's actually doing everything, we can go forward. Or we can produce a graph-based machine learning. Problem with the FPGA programmer. Okay, just let me program this, and then I really want to talk about those two things. Let's patch that. Let's put that in. And then let me put this in bootloader mode. I think we have a crash. And then once it's loaded up. Okay, graph-based machine learning. How does that work, Nathan? So you're traversing a graph based on neural responses or something? Is that like the new ones? Is that like one of the new machine learnings where you're feeding signals back into the thing that is making them? Like the systolic ones or something? Like, I know something like systolic with polyphase filters or something of the sort. No, I have a problem with uploading to the FPGA. Yeah, we'll talk about that in the FPGA stream. You're using a Xilinx. I don't know much about FPGAs. Like right now, I only know about lattice FPGAs. That's all I know. Like, I'm sorry. So, is your FPGA supported by Appio? I wonder. Bartholomew. So let's connect and see how long it actually does it without crashing. Then I'll know. I know why this is happening. I genuinely know why this is happening. I have a feeling. Anyways, we've also found the error with the stream before we even go further. You see, look, our Appio. This one. It's an open source. It's a Xilinx what? Xilinx Spartan. Where do I get supported FPGAs? Let's see. FPGA boards. It's a Xilinx Spartan. Yeah, it's not here. APC5. Spartan. No, it's not here. So I was wondering whether supported FPGAs. Let's see, supported FPGAs. Yeah, it looks like. Oh yeah, sorry. I was looking at Nathan's comment. So that doesn't Appio does not support your FPGA. Look, our app is blocked. It's basically crashed. Here's my feeling. I think the filtering is taking so much time. This operation is taking so much time. This operation is taking so much time that we make a backlog of blocks that we need to filter, and because of that, we can't really. Yeah. Okay. So this is we have to stop a bit. We have to stop a little bit. We don't. There's no need of rushing forwards because we can't really get that many samples. We have to fix a fundamental issue right now, because right now this is not enough samples to do enough testing on this thing. Here's my feeling. I'm gonna answer you. I'm gonna look at your question just now, Nathan. here's my feeling about our code right now. The thing is, I think this is taking too long. This whole operation here is taking too long. And we're trying to do it immediately. I would like to do it at a delay of the same amount. So the way we've done it at work is we do like a 300 millisecond keyword, and then we have an allowance or a delay of 300 milliseconds before we can react to the data. So 300 milliseconds of the audio happens, and then we have another 300 milliseconds to do the sensing, or rather the computation. So what I would like actually to do is to find a way of yielding from this thread into the other thread, to the other thread. Yeah. So sample all three, put them in some sort of message box, and then have another inference thread or filtering thread. Use a memory block again. So we now want another mem slab. Okay, we now want another mem slab. We want to sense the audio and then put it in a message box somewhere. Then we want to set a filtering thread to actually run through that audio and filter out what is. Okay, let's make some notes. Here, let's add question. How to plot a source signal and a filtered signal over UART to GNU plot. Okay, so right now our filter breaks after a few samples. SH, and then let's go back and copy that. Let's copy this. So this is what we are getting. Copy in such a fashion. Should be. So there's that. Our filter breaks like this. And I think the RxQ is filling up because of the delay between filtering and receiving. Can we pass filtering to another thread and handle it there? That's the first question. Handle it in another thread. Handle it there. And then do we need to mess with priorities between filtering and sensing? Okay, so let's explain what the problem is here. You see, every time all these errors, yeah, you see all these errors, these two errors, these ones. They happen, my intuition is telling me I'm taking too long, because when I remove the filter block, this goes on forever. So now I actually kind of know, because because I have a red-green situation here. When I remove the filter block, it goes on completely well. So what this is telling me is filtering is taking up so much time that we're backlogging. And then what ends up happening is the RX queue ends up full. And then once the RX queue is full, we can't do it anymore. We can't, because it's really waiting for us to take the data so you can do something with it. And we're not taking it quickly enough because we take it and we want to decide. Instead of like taking the whole data at once and then going aside and deciding based on it. That is what my problem, that's what I'm feeling is the problem here. And that's why we're actually getting stuck. That's why the app is crashing, because we're doing filtering the moment we see the data, rather than, can we take the data, put it in another memory slab? Yeah? Can we take the data, put it in another memory slab, and then from that slab, actually perform filtering? You know. That's what I would like to do. So we would need an extra, yes, that's what I'm suggesting, Nathan. Read it, put it in our own queue, and then do the filtering from there. But here's the problem. It's not that simple, because now you get Nathan, do you know about real-time systems? Now you get to deal with the real-time system. Your customer, okay? Your customer, you just use my face. Your customer expects you to react very quickly to, "Hey Siri." They expect you to react very quickly to "Hey Siri." Okay? So you have a deadline. We have to do it before the human yes, we can put it in our own queue and deal with it at our own rate, but our own rate has to be faster than the human will perceive that there is a delay. Does that make any sense? This is now a real-time problem, because we have a deadline. Okay, it's not a hard deadline because no one will die, but the human, like, this is things, no, that I don't use that AI. Why don't you use that AI? It's too slow. It never recognizes my audio that quickly. You see, that's what we're fighting here. We can, yes, we can. The simple solution would be to have another memory block. Let's try it. I don't want to make this too long. We already passed the hour of streaming, but let's sketch out a solution and then we'll leave it at that, because now this is why I think we need to do stuff. Nah, that's wrong. You're not supposed to do that. Why are you doing that? There is a compile command, sir. So why are you doing that? Yeah, cool. I think the solution here is to come back here, and then let's actually just build a queue. Let's try and build a queue and leave it at that. Okay? Just see. So what I want to do here is I want to make a new mem slab. I actually don't need to do much. Check this. Look at this. K mem slab static. But I want to build it and see how much more data that we're using. Okay, cool. So first of all, how much are we using? Let's look. So right now we're using 60% of the RAM. Okay, so let's add another one. I think this one will be. I think this one will be heavy. I think we're definitely hitting 90% of the RAM. Define static filter slab. Block size. Block count. So we can even actually just make this a tiny bit smaller and just say 3, because we just we don't want it to be we don't want it to be that big. We really don't want it to be that big, and we know we're only gonna put 3 blocks in it. So, and we can sort of later we can do some math and some delays, and that way we can make it disappear. We can make sure we never put more than 3 in it. So the first thing I want to do is just build it and see how much more RAM am I taking by doing double that. So basically we have to make a message queue on the other side that can hold the information that we want. And then I think the solution would be to now we have to go back to K-mem slabs. It's become a mem slab thing. So the solution here becomes that is handled for us. We want to allocate here, and then we'll remove it later. We will remove it. Yeah. Cool. I'm thinking. When do we do freeze? When do we do allocates? We do our allocates in the reads. So I'm thinking here, every time we read, so somewhere here, let's leave this. This should be commented out right now. To do. Let's do a to do. And then let's put move this to its own thread. Okay, cool. Let's leave it that. Let's leave that there. Do we move that to its own thread? Cool. Let's leave that there like that. So what I want to do here is we'll remove all the comments after it's working. It's easier to remove them after it's working. Copy data so we can use it later. Filter it later. And copy. The moment you start reading, the RxQ sends data. The RxQ is it's a continuous signal from the real world. So the moment you open the tab, it's just giving you data. So you need to get it quickly enough and then stop it. If you don't want it to send, just stop it, basically. But you need to collect it quickly enough. And it depends on how much power you have. You can run them full time and just be clearing them in the background. But right now we're threading needles right now. So here, what I want to do, we can actually do the RS. We can actually do the how do I say this? We can actually do the I squared S thing. We can allocate here, and we can expect the consumer thread, which we don't know right now. We haven't made it yet. We can expect the consumer thread to free this thing. So we don't have to free it ourselves right now. All we need to do is allocate it and use it. So cool. So we already have some sort of block pointer. Yeah. Okay, cool. Do you have is there a way of copying from one mem slab to another? One thread to another. That's that's fine. That's fine. Yeah. So is there an easy way of just copying from one mem slab to another? Because what I'm feeling here is we do a mem slab, a lock, and then in here we want to do and filter slab, and then and then inside the filter slab we want to do void, and then it's a void pointer to pointer to a pointer, because it wants we want to cast this all. So this is an address of an address. Void and then you can say here, and wait, let's see, let me just make a new one here. We can void filter block. So we can say void filter block, and I think here we can something filter block. Okay, I'm just being careful. Okay, no, wait. Yeah, and then that should do that. And then here, this mem slab a lock. And then in here, yeah, I want a mem set. Mem set block pointer with something. It gives a mem set block pointer, and then you say we want to say the value and the size, so that you can go like mem set. Nathan, you have a question. Also happens if you free the mem block before applying a filter. Well, that's what we're doing right now. It just runs it runs normal. It just runs. It does the thing it's supposed to do. No, that's not the one I want, because this actually no, that's not what I actually want. I want to copy from mem block copy between mem blocks. No. Okay, so I need to find out how to copy out of a mem block or how to read a mem block. I know the size of the mem block. But I don't want to walk it. I don't want to walk it because walking is what gives us problems. Whenever we walk things, this costs a lot of time. This costs a lot of time. Actually, what if we just don't do all of this? What if we just don't do all of this, actually? Does what need to be in its own thread? Yeah, actually, that's a good idea. This comment starts here. Okay, cool. This is actually perfect. So that's fine. That's okay. Cool. This actually works out the way we wanted it to do. Um, so yeah. Yes. So here, this becomes the thing we need to do. Move data manipulation to its own thread, all of it. That's actually what needs to happen. And then this can go like, yeah, dd, and then we can remove this. And then all this does is copy audio data to new thread. That's what we need to do here. That's what we need to do here. And I think the echo sample I2S Zephyr I2S echo I2S echo sample I2S echo sample. Yeah, this one does something of the sort. This does something of the sort. So in this one, I'll show you. Yeah, sort of. I can see now. Now I'm starting to understand why they do things like that. So this one, this is quite odd. So I'll just scroll down to. I remember now. Prepare transfer. That's no. There's let's see. Where does it read? I want to see the read. Yeah, and then it uses semaphores, so it blocks and opens gates for things to happen. Process block data, you see that one? What happens here is it takes this memory block and it does something with it. You see here? We sort of copy it over, and I sort of knew we would have to walk that thing. So you see, we make a sort of echo block. Where is this echo block coming from? Yeah, we make an echo block. We make a new block. You can also test this with a native sim. You can go in Zephyr. Okay, I don't know how bad I messed that up, but somehow I did. What is happening here? What is missing? Slab must be aligned. Yeah, I knew it. I knew it. I knew it. Another thing for Bartholomew. So you can't make a slab of this. A slab has to be 4. That is basically the minimum. Yes, that's the thing. So you need a minimum of that, and that will. Nathan, you can't. You see, when I'm building, you can use this. I'll give you native sim Zephyr. You don't need hardware to. You don't need hardware. Yeah, that please. You don't really need hardware. You can use native Zephyr. Native. Yeah, that one. You don't really need hardware. You can use native sim, and native sim is let me see, somewhere here. Must be somewhere, something I've clicked before. Yeah, Zephyr has device emulators and simulators, and you can basically use one called native sim, and it will you can test this. It will use things inside it will emulate the board that you want to replicate inside your laptop, and then whatever, or desktop, or whatever computer you're using, basically. But anyways, as I was saying, there is an echo block. They copy over. So all of this time I'm using here, all of this time I'm using here, all of this time that I'm using here, all of this time that I'm using here, I can just copy samples over to another block. And actually, I don't have to use a memory block. I don't have to use echo block. So echo block is just one, which actually works for us, doesn't it? Doesn't it? Because we only have one memory slab, and then we have one echo block that we use later. Yeah. Okay, I'm gonna go through this code and then see how they copy over the data. So all of the work that we're going to do here is basically just go through all the samples and copy them over. We can even actually do the floating, because that's float is just one. It's one cycle, so we can't lose that cycle. It's fine. We can lose that cycle and not actually have to not suffer so much. Not suffer so much. So yeah, I think the next steps become copy over samples to their own block, process that block. This is how we use Bartholomew's hysterectic detector. So yes, this works. Yeah. Yes. Plan. 1. Copy block samples to filter block. Okay. No, it still doesn't work. It still doesn't work. Unless the thing actually yields. when it reads. Unless the thing actually yields. If there's a yield happening when it reads, then it's fine. But even if there's a yield happening, we still need copy block to filter blocks. Use hysteresis detector in filter thread to maintain noise or no noise state. Do inference in filter thread. Yeah, we need a different thread. Because we need to copy all over these samples quickly, put them in their own thread, and then in that thread we can run the filter, and then when we are running the filter, then we basically don't cause these errors where we run out of RX, where the RX queue doesn't block up. So because if the real world signals are just happening, and then we need to give ourselves like a good gap. So we'll say we will detect a keyword. If it's a 300 millisecond keyword, we will have the ability of detecting it, say 300 milliseconds after it happened. That gives us enough time to go and collect 300 milliseconds of samples, and then we can sit on the side and do 300 milliseconds. We have 300 milliseconds to filter the samples, do some computation on it, and give it back. And I think that is actually not so difficult because the filtering, although it's an expensive operation, it does not take as long as collecting all the samples, because collecting all the samples is very expensive right now and it's very time consuming. So we have to do it when they're happening because they're real time. You can't pose the voice of someone so that you just sense what they're doing. This voice just comes in. So that's very expensive to collect. Once we collect that and we use that, we can put it in a different thread and we can do the computations much quicker, because the computations don't have to take that as long as collecting them, because there's no this thing again. Yeah. Okay, I'm gonna stop there. This is becoming a long debug session, and I need to go and read. But the plan is take this data, put it in its own. We basically need to build a filtering thread. Copy data over to the filtering thread, and then the moment the audio thread yields, we activate the filter thread. And then when the filter thread is activated, it goes for it from there. So now, basically, we need to add a new state in our system, which is, we need a recording state, and then we also need a we have a state machine we can use. Yeah. So let me add some notes here. Perfect. Can we use the state machine to transition from capturing audio to filtering audio? Yes, because that's what we need. This is exactly what we need. So the problem was, as I've stated here, if we added a new thread for filtering, do we add some sort of priority so that when it finishes capturing, it goes straight to filtering? And that's a problem, because you don't know. Something more higher priority could happen in the Okay, cool. That's awesome. Bartholomew, if you find a race condition, please open an issue. Even if you're gonna fix it, that's fine. Please open an issue and then we can record it and we can go through the stream and try and fix it. But here's the thing. So this is where our state machine becomes really, it actually helps us. Our state machine allows us to know when we're in mic capture, whenever we finish mic capture, we go straight to filtering. And then we can also add a semaphore that does not allow us to capture data while we're doing filtering. And what does that do? The semaphore blocks the recording, so we can't remember the sensing thread is just consuming data. So if we add another, we don't even need to add another semaphore. We need to use the same mic sense semaphore and block the recording when we are doing filtering, so that it can't capture. This is I understand it. This is why they're doing it here. This is exactly why they're doing it here. So whenever they're look at it here, look at it here, look at it here, look at it in this sample. Oh wow, this is cool. There's a transfer. There's a transfer semaphore. This transfer semaphore allows the recording to happen. And if it's not, if the other thread, our filtering thread now, is doing something, we should not allow recording to happen. Because if recording happens while we are filtering, then the memory blocks, the very memory blocks that we are operating on, they can get corrupted. So the other thing we're going to do is we're going to use the state machine to move from recording to filtering. And then once we're done with filtering, we can allow recording to happen again, basically. Okay, so now I need to go through this sample and see how they're doing it, write down a plan, do some research, and then that's probably what we're going to be doing tomorrow. Oh, this is amazing. This is amazing. I understand. It's not unnecessarily complicated. It's actually just what it needs. And then, okay, so there's the other part. We added another mem slab. It was big enough that we're building and we wanted to see. Yo, how does this go less? The samples is unused. That's fine. Filter block is unused. Yeah, but how does this go less? How does this just go less? Percentage used went to 47 after we added the thing. Not. Anyways, it was 60 before. Anyways, I'm gonna stop the stream there. That has been a really long one, and I need to go and chill out, and I need to go and pick some flowers for my wife and stuff. But I'm gonna stop the stream there. I'm gonna make a plan, and this is what we're going to do tomorrow. So tomorrow we're gonna cut it out, move filtering to its own thread, add a new memory block that we fill from there, and probably use the state machine to move from recording to filtering, and vice versa. Yeah, that's what I'm gonna do. Thank you so much, you guys, for coming today. That was amazing. This is amazing learning. It's amazing to retroactively or backwards to sort of like start to connect the dots in how other systems are built, and for those problems to become real, and for us to use those solutions in our code. Yeah. Nathan, I didn't forget about your back propagation. We'll talk about it. Once we get to a place where we understand FPGAs well enough that we can build and implement very basic neural processors on them, we'll probably do it. We'll probably do we'll go back to the machine learning thing. But anyways, thank you guys so much. That's been amazing. This discussion has been amazing, and it's been good to discover the problems that we're facing and to have a plan forwards. Yeah, see you guys later in the day when we do we add some, what is it? We're going to add some instruction decoding from the RISC-V architecture to our tiny CPU later today. But other than that, thank you so much. Cheers for coming today. See you later. That was amazing. Yeah, cheers. Amazing.